All right. The next type of separation technique is going to be extraction. Turn that light on for a second. All right. You're going to use a separatory funnel. All right, and I'll show you this thing how this works. All right. Right now it has a dye in it. 2,6-diindophenol or something like that. You don't have to worry about that. But notice it doesn't separate out. I got that color in there so you can see that. You won't see that in the lab tomorrow, but you can, because it's basically going to be invisible. The caffeine we're going to try to extract out of Coke or Monster or Amp or whatever energy drinks you try is going to be invisible. You can't see it. But this food color, or not food coloring, but it's a dye. I can see that it only dissolves in the top layer, not in the bottom. Now that's the theory behind this. Notice it's similar to chromatography you just did. The difference is chromatography took advantage of the polarity differences and the solubility differences, but it had a stationary phase, the paper, and it had a mobile phase. Well, in this case, both phases are liquid. I don't have a stationary phase. All right, so when you do this tomorrow, you have to find a way to extract that out. And I'll show you all the procedure, and hopefully you'll listen. All right, turn that light off. Basically, a theory first. What is an extraction? Well, it separates a mixture by virtue of the different solubilities, as you'd expect. And solubility is dependent on polarity.
It's driving me nuts.
Okay, solubility depends on polarity. All right, now the difference between an extract, so does chromatography. All right, we've had a lot of different separation techniques we've used over the years. We use boiling point as the property we're going to use, and then we did that for distillation, alcohol and water. We've used just solubility in a very rough sense in decanting and filtration. Sand is not soluble in water, so we were able to filter it out, so filtration, or even decant it out. In this case, the difference is you're using solubility again, but both phases are liquids in this case. All right, and because of that, we have to do it a little bit differently. We have to use a special equipment called a separatory funnel. All right, it's used often to separate out inorganic and organic substances. Now, when you see the structure for caffeine, you'll see that he is pretty much organic. He dissolves enough in the soda to dissolve in there to be able to drink, but it would dissolve better in chloroform. It dissolves better in a non-polar substance, and so that's why we're going to use chloroform to extract it out of our soda. Okay,
That's why you don't spill it.
and you don't spill it, right? Okay, look here. We got two different phases. They're both labeled on your thing, I think. And this is how it's going to look for you guys. The chloroform is actually heavier. It sinks to the bottom, all right, which is kind of unusual. Usually if you see a separation like that, like, for example, you can see this in a vinegar and oil salad dressing. Usually what's on the top? Yeah, no. What's on the top?
I got you.
Oil floats, right? So the oil will be on the top and the water's on the bottom. Water's more dense than oil. All right, but chloroform is unusually dense, and basically it will sink to the bottom, and that's where you're going to find it. Matter of fact, that's what this looks like right here. Let me see if I can see this well. Here, turn that light on. Turn it a little bit. All right, and if you look at this, you can see the two layers are obvious because of the color. All right. Now, if you look at the picture of caffeine's got a lot of organic portions to it. CH3, CH3, CH3. Even these carbon bonds and the carbon M bond is not very polar. The only thing that would be considered even partly polar would be the oxygens. All right, so although it will dissolve enough in water to drink it, it's not really as soluble in water as it is in chloroform. So what are you going to do? Well, let me show you something here. This is kind of neat. All right, I mixed this up originally with the other class, but I'm going to use the same one so I don't have to waste anything. Right now, I've got a dye, which I guess I should show you the dye in how dark of a blue color it is. Okay, this is the dye. It's a small amount. I only added about 6 milliliters to that thing, so I added about maybe that much to it. All right, and then if I add water to it, you'll see how strong of a dye this is. I mean, it's a very deep blue purple. From just a few drops of that dye, it turns very deep blue. All right, now that's what you see here. When you go to do this tomorrow, here's what you're going to do. All right, you're going to have your soda, basically, and water and ammonia, a couple of things in there, and you're going to have that, and you're going to pour it in here, and you're going to add some chloroform to it. You put your hands over the top. Make sure this lid's on nice and tight. Okay, and then you're going to turn that upside down, and as soon as you add these guys together in the fume hood, you're going to tap it so there's no stuff here, and then vent it, and you'll hear a little pop, a little pressure being released. All right, and then if you shake it up, no matter how much I shake this guy up right now, that blue's always going to come back to the top. All right, you just have to trust me. I don't want to get a whole lot of bubbles in there. What I'm going to do now, though, is make this guy more polar than non-polar. I'm sorry, more non-polar than polar. Right now, he's in the aqueous phase. He's in the top layer. Oh, I'm going to go back. He's in the top layer. He's up here. You can see the blue is up here. Okay? Watch what happens when I change his pH. I'm going to add some hydrochloric acid to it.
It's like orange juice.
And I add the hydrochloric acid. What's like orange juice? There's nothing that looks like orange juice here. Anyway, I add the hydrochloric acid to it. And if you watch, I stir it up like this. See what color it changes?
Oh. Like orange juice.
It's red, actually. All right, so now it turns red. All right, now,
That's cool.
if I put the lid on, watch again. As soon as I put that lid on, I want to put my fingers over the top, tilt it upside down, tap it a little bit, and vent it. You can hear a little pop there if you're sitting up front, probably. All right. Make sure you don't pull this stopcock off either. Then you'll shake it gently at first, tap it, and vent it. Okay. Shake it.
Yeah, shake that.
Tap it. Always tapping because you don't want stuff here. Because what happens if it's stuck here? It's going to go shooting out when that pressure is released. All right. Eventually, you'll shake it a little bit harder. All right. But eventually, what's happening to this red color is watch what happens when I set this guy back up. Okay. Venting it one more time. And you'll be doing this for about 3 or 4 minutes probably. I'm only going to do a little bit. So all you want to do is see this. Vent it. Of course, some mistakes people make. Stopcock is closed when it's like this. Okay? And it's open this way. If I start shaking it when it's open, what's it going to do? Second mistake, not putting my fingers over the top. My fingers aren't over the top of this. What's that stopper going to do? It's going to come off. Okay. So one more shake. And
shake it. Tap it.
We don't have to tap it now. All right. It's pretty much the pressure has been released. I put it back on. Where's the red now?
On the bottom.
It's on the bottom. Now here's why. When litmus or phenolphthalein or any of those guys we see as indicators turn color, they are turning color because there has some molecular change. All right. In this case, that molecular change, that change in their structure, all right, with the pH, actually caused him to become more non-polar. More organic. It dissolves better in the organic than he does in the aqueous, and that's why he's down at the bottom.
Why is the top part like cloudy now?
It's just because you shake up water, it's going to get cloudy.
I don't think so.
Anyway,
Shake up water.
so look, if I right now I can't see this tomorrow when I'm doing the caffeine, but right now I can see that I've got the red is down here. Now, you'll be extracting that off. You won't be able to see the caffeine, but you'll extract off just the bottom layer. You'll put this over a Petri dish, extract just the bottom layer into that Petri dish, and stop when it gets down to this level here. All right? We'll let that evaporate in the fume hood, and then you'll see the crystals of caffeine that you will have formed not overnight, actually, just in an hour or so.